Welcome to Lab 5. This is our last in a series of experiments to investigate the conservation of energy and other things. Our Lab 3 was all about the conservation of energy as you smash things into each other. The Lab 4 was all about the conservation of energy when you transferred it from kinetic to potential and back again. But you might have noticed something a little weird, and that's that none of these measurements were perfect. We never measured perfect conservation of energy. It was always lost somewhere. Now, you've probably already guessed that this is due to this thing that we call friction. There's some sort of dissipation into the universe that energy has a tendency to do. The goal of this lab is to show you that this dissipation, this friction, is not some mysterious force, but it's really just the conversion of this mechanical energy, the potential and the kinetic, to heat. And that heat is measurable. We can measure the temperature of our system and thus account for the energy that we thought was being lost before.
We're ready.
So in order to account for this dissipation, we have a system that allows us to put in kinetic energy by turning this crank and convert it to potential energy of the bucket. But notice that no matter how much kinetic energy I put in, we're not gaining any more potential energy than a little bit that's being put into lifting the bucket about a centimeter. So where's the rest of the energy going? What's happening is it's being dissipated by this loose connection here between the rope and the barrel. Now, you might wonder, well, how can this help us account for the energy that's being lost? And the key is that in this barrel, there is a thermometer. It's really just a resistor that depends on temperature. And by measuring the resistance, we can measure the temperature of the barrel. And because all of this extra heat is coming directly from the dissipation of energy from turning the crank and this imperfect connection between the crank and the rope, because of this, we can account for all of the energy that's being lost, that's not going into potential energy, that's just being a useless crank at the turn that's only heating up the barrel. So the actual procedure is quite simple. All we have to do is turn this crank and count the number of turns that we do. This will give us a measure of how much kinetic energy we're putting into the system. The next thing we do is time how long we've been turning the crank for and measure the temperature every 30 seconds. So, if we're ready to begin.
We're ready. Press the button.
And 92.2 ohms, kilo ohms.
17.
And 88.2 kilo ohms.
26.
And 91.0 kilo ohms.
37.
37. And 89.9 kilo ohms.
It's probably fine.
You may have noticed there that as the barrel heated up, as we were turning the crank, the resistance that we were measuring was decreasing. This is for the very simple reason that there's a decreasing relationship between resistance and temperature, which is given by this table here. From this resistance, we can calculate a temperature, and from the temperature, we can calculate how much work we are putting into this device, and how much work is not being put into raising the bucket, and thus how much energy is being dissipated.